In this module, we will learn what a couple is. So a couple is a pair of forces that are equal in magnitude, opposite in direction, and are along different lines of action. And let me ask you a question right now. Do you think a couple is the same thing as an action-reaction pair of forces? We'll discuss that in class, but think about it, please. Now, I'm going to take this chance to review something we talked about in the first week about using scalar versus vector notation. These are two different ways of drawing the same couple. On the left, we're using the scalar notation, in which case I use the arrow as the direction, and the symbol F scalar is the magnitude of that force. Whereas in the right, I'm using the full vector labeling, so I'm using the name F vector, meaning the F with the underline on the left, and the other vector being its opposite is negative F. And this might be confusing because you might say, well, how come on the left I don't use the negative sign? How come on the right I do? Well, it's because on the left-hand side I'm simply using the magnitude as the label. On the right-hand side I'm using the full name of the vector as the label. And so notice that a couple has a property that the sum of the forces of the couple is 0. And if I use the scalar symbol or the scalar labeling system to show this on the left, I'm going to make a unit vector called u, which is parallel to the left vector. I'm going to sum the forces in the u direction. I'm going to get F minus F equals 0. And on the right, using the vector notation, I'm going to sum the two forces. The sum of the forces is F plus negative F, and that equals 0. So either way you do it, you find that a couple has a net sum of 0 force. However, there's something else special about a couple. We're going to explore it right now, and the couple does create moment. And in fact, an interesting property about couples are that they create the same moment about any 2 points you would pick. So for example, if I pick a random point here called P and one over here called Q, the sum of the moments of those two forces about the point P is the same as the sum of the moments of those forces about the point Q. To show this, we're going to do a couple experiments. We won't do an actual complete proof, but let's say I have, first of all, a distance d that defines the perpendicular distance between those two lines of action. I'm going to distinguish each vector with a number, even though they have the same value. I want to say one is F1, one is F2. That way I can see in the calculations what I'm talking about. And then I'm going to define 3 points, P, Q, and R. P happens to be on the line of F1. Q happens to be on the line of F2. And R happens to be at some other point, a perpendicular distance h away from the second line. So let's do an experiment. Let's take the moment, or the sum of the moments about the point P. And again, P is over there. Let's again recall our positive convention for moment is counterclockwise. If I now sum the moments around the point P, I see that the force F1 goes through the point, which means it gives 0 moment. And then the force F2 causes a clockwise sense. That's why there's a negative sign there. And it's F2 times d in magnitude. And now I say that's equal to negative F times d, because after all, F2 has the value of F. If I now do the same experiment about the point Q, same convention for positive. In this case, I see that it's now the vector F2 that passes through the point Q, and it causes 0 moment about Q. The vector F1 causes a clockwise moment about Q. That's why, again, there's a negative. And F1 equaling F, the final sum of the moment about Q is negative F times d, the same that we had before. And now if I do the sum of the moment about the point R, once again using the same positive convention, in the sum of the moment about R, the force F2 in this case, makes a counterclockwise moment about r, so it has a value of F2 times h, but the F1 force is now still clockwise about the point r, and notice its total distance is now the d plus the h, so it's negative F1 times h plus d, and if I think about this, I have F2h minus F1h, and because F1 and F2 have the same value, they cancel out, and so my final result is negative F times d. So in summary, no matter which way you do it, you get the sum of the moments about any of those points is negative F times d. And this is our key idea about a couple. Now, in summary, a couple is a pair of forces such that the sum of the forces is 0, and the sum of the moment about any 2 points is the same. And what this means is that we can now associate the couple with what might be called a pure torque or a free torque vector or a free moment vector. The torque does not push or pull, but it has a sense of rotation. Imagine your hands like on the sides of a steering wheel, okay? And so the action of this pair of forces is equivalent to a rotational motion, and we've seen now before that its strength or its magnitude is F times d. So whenever we see a rotational symbol, because the couple in our theory has the same value about any point, it turns out I can locate this about any point that I want. And this might sound strange, but this is a truth that we have to start getting accustomed to. A free moment vector represented by a curled arrow, or sometimes we refer to this as a pure torque vector, it has the same effect about any point in the plane.